And at the end of the last video, I kind of lied. We had one more page. So here are some more examples of histograms with box plots underneath them. So hopefully it'll make sense to compare these. Like this first distribution is approximately symmetric, definitely unimodal. And if you look at this center part there, that's the middle 50% of the data. And where does that match up on the histogram? Basically these 3 bars, maybe not quite all of those, but I think you can visually see that that's definitely the middle 50% of the data. And then so this 25% is pretty small, and then this 25% is quite bigger. Same on the upper side. That kind of shows, that goes along with the tapering. There's less data values as you go out further, and so that stretches out your box plot. Here's one that's a little more uniform. It's not exactly uniform, but it's definitely not unimodal. It's multimodal. And look at the widths here. These are very much more alike than these would be. So a uniform distribution is going to have an equal width kind of these 4 sections of the box plot. Here's a skewed one again, and notice on the skewed ones, on the upper end of this where most of the data is, these box plot pieces are just squeezed together. So there to there is 50% of the data. That's going to create a tall bar. And then where we have less data, it's going to be spread out further on the box plot. Here's a little one this one's a little bit harder to interpret, but if you think right there, that narrow space in the x value direction has to have 25% of the data, and that's going to give you a tall bar is what that's going to do. And then we have some outliers on the right end here. This tapers off on the left, so it spreads out a little bit more. And just a few more, a couple more examples here. Again, right skewed, and you can see that it creates a whisker that's very long. And some other, histograms compared, box plots compared. One of the important things is that the scale, the X scale, is the same for all of these comparisons. Otherwise, how could you compare them if the X scale wasn't the same? It would be very misleading. So make sure that your X scale is the same. So quickly, an important fact to know. When the distribution of a variable is skewed, then you want to use the median and the IQR, interquartile range, to determine measures of center and spread. You don't want to use like the average of the data set or anything like that. Median and interquartile range are the best descriptors of this data set. The reason why is that the extreme values, the very extreme values in a data set, say like this value or that 12 on the girl data set from earlier, that one single value doesn't really impact the mean very much because it's just one data value out of 14. The median is probably going to still be in the same place. Interquartile range, the middle 50% of the data, it's probably going to be in the same place. In fact, if the girl had a low score of 12, the mean in the interquartile range would be in the same place, whether her score was 12 or if her score was 2. It doesn't affect the median and interquartile range because they are like placeholders. They're just where the placement of each data value is. It doesn't really take into account the value of the actual value of the datum. So we can write this out. Extreme values do not influence median and interquartile range. However, the mean or average will be influenced by extremes. So if you took severely skewed distribution and tried to find the mean of it, it's going to be influenced by these high values. The high values will pull the mean to the right. Same up here. These higher values are going to pull the mean, the value of the mean, to the right. It's going to pull it to be a higher number. The other vocabulary you need to know here is that the median, I spelled it wrong, the median is what's called resistant to outliers. The median is resistant to outliers. In other words, outliers don't have a big effect on it. Okay? Alright. That is the end of the notes.